Yeah, I have to apologize. My German is not nearly good enough to give a talk. I can understand some, but it would be comical. I'm going to make some jokes, but not that kind of joke. So my background is varied, as the man said. I work currently with MapR Technologies and also with Apache as one of the board members. I'm also an O'Reilly author and enthusiast about all kinds of things, but especially computing. You can reach me, of course, by multiple methods. In fact, I've arranged so that almost anything anybody has ever guessed for my password or my email at MapR will work. So my background is to do with universities and startups. I forget, I'd have to count how many startups, 5 or 6 now. All were looking at how to push the bounds of technology in terms of learning, in terms of interacting with people, either large-scale consumer sorts of things or financial sorts of things. So I alternated between having 30 million customers and 30. At MapR, we kind of split the middle, the geometric mean there. And I've been involved in open source, and I'm passionate about that for a very long time, since the mid-70s, before we knew what open source was, when it was just, I handed him a floppy disk, that sort of thing, and he worked on it and handed it back. But it was that idea of sharing, that idea of going to a cafe and talking to people and learning from each other that I think was the true heart of open source. And it's different now, but it's the same. And I continue to work in that to the detriment of sleeping, but I'm excited about it still. Now, for the talk today, I want to emphasize there is no magical formula for success in bringing advanced applications into production. Now, that is not to say that there isn't a formula. It just isn't magic. There is actually a lot of things that are consistent for different people putting things into production. It just isn't magical. People will tell you it is. People will tell you that this system or that system, the latest machine learning, the latest orchestration framework will make it all better. It's still very hard work. But there are still some very important steps that you can take that will make it much, much easier to be successful. And these are the answers. We'll talk about the questions in a moment. So one of the tricks is to be ready for the second project. The first project that you have in these either advanced computing or large scale typically needs to be boring, but with a very high probability of success. It's the second project that will make you the hero in the company. And so you need to be ready for the second project. You also need to think seriously about how reliable a system must be. The Google site reliability book makes a very good point that if you guarantee 3 nines, you better make sure your system is down sometimes. Surprised me. I always thought we were supposed to make them stay up. But their point was that if you only guarantee 3 nines and you deliver 5, if you deliver 100% uptime for 2 years, people will depend on it. And you will then have to pay the penalty of supporting a 5.9 project, even though you only promised 3. And so if you promise 99.9% uptime, you should make sure that your users understand that it's not only that. And so you have to decide, what do you want to deliver? We had this discussion just last night. AWS burped and our website went offline. And one of our engineers is saying, we need to use multiple clouds and multiple instances in both clouds and redundant DNS and all this. I'm going, wait, what if the website is down for 1 hour a year? How bad is that? Is it worth all of that effort to take it down to 5 seconds? Probably not. But there's probably more important things we could do. So it's important to think about SLAs. Does it take an army? as a point of reference, one of our large retail customers, very large retail customer, uses 3 people to administer roughly 2,000 nodes for a large data system. 3 people. The system is reliable enough that they do not have a call rotation schedule. Everybody is on call 24 hours. There has been no call for 4 years, so that's nice. But the point here is you need to be able to have a division in your organization. I'll talk more about this in a bit. A division below which the scaling of the manpower, the people power, with scale and size and number of applications is almost 0. Now the counterexample is at Netflix they claim to have 5,000 nodes of Kafka, organized in 5 to 20 node clusters. Which, if you do the math, means they have hundreds of clusters, each one of which takes some fraction of a person to administer. So that probably means they have dozens of people doing this, and the number of people administering their clusters scales with size. Infrastructure force should not scale with size. Application level should, and that's where the resources should go. So we'll talk about that. And can you adapt? Can you change things? Does your system deliver value? So the way that people usually address these questions is by talking about what a system can offer. Does it offer multi-tenancy? But people don't understand why they want it. So we should give the answers first. Can you succeed on the second application on the same sunk cost hardware and software? Can they live together so that the second thing can be very high risk? You don't even have to tell people you're doing it. Can you get the basics in place? Can you access from a hybrid cloud, multi-cloud? Because if you have 1,000 machines on premises now, it will take years to move to cloud. So for the next few years, you will at least be hybrid. There's no choice about that. Do you have flexibility and agility? Do you have good ROI? Now, when it comes to AI, there's some basics. Who here has built a machine learning system? I mean, amazingly enough, 2 years ago, 2 people would have raised their hand. And look, now it's 80%. This is a big shift. Now, you've seen this picture then in some form. You put old data in, you have a magic machine, and you get a model out. And maybe you get a PhD. And then you put more data in to the model. The model is a program, so this is a form of programming. And you get magical decisions out. And of course, world domination follows. This is the common view, but this is almost completely wrong. 90% of the effort is not on that picture. We spell it Logistics, but of course, English is a very difficult language for spelling and pronunciation. The pronunciation is bullshit. That's where your time goes, is in the preparation of the data, in the deployment of the systems, in the management of them, in the monitoring of them. The learning is a very small part. But the careful and important lesson here is that if you're not careful and do things well, that 90% can triple. And so you have oversubscribed all of your resources, and there's 0 time to do the learning. The lesson is to do the logistics as efficiently as possible so you do have that 10% to do the clever things. No group I know has more than 10% serious data science. So, as I said, getting data is hard, and this idea of the model is nonsense. You will immediately have a new version of the same model. Then you'll have 3 new versions of the same model. Then you'll have a reference stable version of the same model, and you will want to be trying things. And then you will have 100 different functions that you want to do, so now you have 1,000 models. The idea that you will build one model and everything will be beautiful is complete nonsense. And so, again, the logistics of this become much harder. So lesson number 0 here that I want to highlight, and of course we're all computer scientists, so we count from 0, is definitely sweat the little things. Now the business people say, don't sweat the small things, think big picture. Logistics, that's just logistics. You know what I mean. It is really important to get the simple things, the small things, to be small. They will grow big if you let them. They will get in your way, they'll make everything have high friction. It's way, way more important to get those small so you have time for the big things. In computing, there is no choice but to have things work. So let's go in and talk about some patterns and shapes that I've seen in successful production systems. First one is getting the data right. And this is an odd lesson, and because what we're doing with data science, what we're doing when we build models, is we're writing programs. We're writing programs without semicolons, with now mathematics. We're writing programs to solve problems that we do not understand. Now, by definition, this is true, because if we understood the problem, if we understood what fraud looks like, if we understood what people really wanted, we would just code it. It would be much simpler to do that. And so machine learning is like a broken form of coding. Broken because we do not know the exact answer. We can only approximate the answer by reasoning from examples, by reasoning from real data. And it's a way that we can code things before we truly understand them. And maybe we never will. Maybe we will never understand what a fraudster will do tomorrow. Maybe we will never really understand musical tastes of everybody. I've seen recommendations that I just didn't understand, and I brought somebody over and I showed them the recommendation. They go, yeah. And I go, why? And they go, oh, it's obvious. And this will always happen. And so the virtue is we can do this. The vice, the problem is that we can do this. Code gets carefully examined, carefully reviewed, carefully tested. At least it should be. Who here does all of this exactly perfectly? Maybe not me. A lot fewer hands than with machine learning. But it does get more care because you know what it's supposed to do. At least approximately, at least if you didn't misunderstand the product manager. Could never happen. If they knew what the right answer was. But it's a much simpler task. And so you can audit it, you can test it, you can have a release process, you can have an exit criterion. That's very simple. But it all depends on knowing what we want to do. Machine learning is a very different animal. Because we do not know exactly the right answer, we cannot test it. There is no unit test for machine learning. We can save some of the data and see how it does on that, see if that works, but we cannot give it tomorrow's data and see what it does. With code, we can do that. We can build a unit test that says this is the extreme, this is the extreme, this is the induction process, therefore it's correct. Cannot do that with machine learning. We have to try to work from this data, and we have to use as much version control as we can. We can version control the learning system. We can version control our feature extractors. We can version control our building process. But it's very difficult to version control the data. I give you 5 petabytes of data, you extract 10 terabytes, and how do you put that into Git? Doesn't happen. Now, this is very, very important, because what's happening here is with data, we start gathering data. It's not production, doesn't matter. We gather, it's nice, we gather it, we're looking at it, trying to see patterns. And what happens then is this terminator comes and appears next to us. It's ourselves from the future, from 1 year from now, comes back in time and says, oh, your data is now in production. See, You can put data into production retroactively. You can one day say, I'm going to build a machine learning model, and now all of my data for the last year is my training data, and even though I didn't think it was in production, now it is. So data is a very difficult thing. We need to control things like the training process. We need to be able to version control the actual models that we build. But what about the data? We have to be able to version control that just as easily as we do code. The classic case is the CEO comes in and says, why did you recommend pink waffles this morning? You embarrassed me in front of my kids. Who wants pink waffles? Why did you do that? The traditional data science answer is, well, shit happens. You know, that's the answer. You don't like it. But the better answer is that you go back and say, give me 20 minutes. And you go back in and you look at exactly what changed from this model versus yesterday versus last week. What happens with new code, old data, new data, old code? When did pink waffles become recommended? If I give the old models the same situation, what would they say? And you can come back and you can say, they've always recommended that. You just never looked. And you could say that authoritatively. That's the goal. That's the place you need to be. And to do that, you need to be able to retroactively put data into production and snapshot it, freeze it, so that you can control it. Success in production starts long before the code for data-intensive applications are written. Code only goes into production when you release it. Data goes into production when you never know, long before you think. So we have to control the data as much as our code. Pattern number 2. Cloud, cloud, cloud. I mean, everybody talks about clouds. They name conferences after it. It's so fashionable. For people like me, being fashionable is very difficult. It's a big burden. I've never trained for this. I don't understand how to be fashionable. And the fact is, though, that the ideas of cloud are very valuable. We want to be able to apply those even if we don't go to the cloud. The core ideas are actually very, very good. They're not just fashionable. Let's take Kubernetes. Who uses Kubernetes if they're going to do orchestration? Who uses something else? So there's one. No, he's just wiggling. And this is the trend that I've seen. 4 years ago, well, 4 years ago was barely the release of Kubernetes, so nobody was using it. 3 years ago, it was up to 30 or 40% at Azure. 2 years ago, it was 70, 80% of new production clusters, and now it's almost overwhelmingly Kubernetes. I've seen the same thing, especially in Europe. Corporate customers here are overwhelmingly adopting or switching to Kubernetes. So let's just take that as the orchestrator. The idea here, and this is a magical view, it's actually a little bit more complicated than this, but this is the magical view. We're going to deploy applications somewhere in our group of machines. We're going to start other applications either close together or far apart according to affinities. We're going to be doing all of this, and we will use Kubernetes to name them. So think about this. The key properties here are that the applications are placed in rational places. Maybe they're moved around in the cluster, and they are named. This is the core function of what Kubernetes is doing. Well, it's doing more than that. It's guarding them and some things, but this is the core idea, is things get placed within our cluster, machines get reused as possible, as practical, in order to make good multi-tenancy happen, and things get named. Now, applications need data. In order for Kubernetes to succeed, the applications must be lightweight, because it needs to be able to move things, stop something, restart it over here. It needs to be able to have that agility in order to succeed. But the applications need data. They need to communicate. The RPC, which is direct from one process to another, has no persistence beyond the two applications, and it's handled by purely networking. That already works. But data outlives any application, and it certainly outlives any container. But that's a real problem, isn't it? Because it's a different life cycle, it's not managed the same way, it becomes heavyweight, it breaks the assumptions of Kubernetes. So what we want to do is we want to be able to have tables, streams, files that are accessible from these systems. And in fact, what we want there is a data platform. You can see a duality here. That data platform needs to be its own opaque entity, just like Kubernetes is an opaque entity, or largely opaque. The data platform needs to move data to the right place to avoid collisions, to avoid too much activity on one node. It needs to name the data, so we have some universal way of naming things. That's exactly what Kubernetes does. So we need something like Kubernetes, but for data. It's an odd thought, but that's really what we need to move to this next layer. Now, there are beginnings of this in various places, but not very many full-fledged applications of that. Another pattern here that I see with very successful customers is they use streams ubiquitously. With microservices, you can connect things in a synchronous way via RPC, and the two services are independent in that you can deploy them independently. That's nice. Even better is if you don't need the answer now, if you just need the action to happen sometime later, you can make these asynchronous by connecting them with the stream instead of an RPC, instead of REST, instead of gRPC. You can use a stream between them. But you can extend that further. So let's talk about this. We have lots of events, and let's not talk about database updates. Let's talk about business level events. They happen for different times for different customers. We may need to reconstruct things. What happened just before you had a problem? And if we think about fraud control, say, it's a system that I've worked on many times. There's time passes for a single user. At some point in time, we detect a fraud. Somebody has stolen money from this customer. That means that sometime before we detected it, the fraud occurred. And hopefully, there was some time before that we could have prevented it. Makes sense, right? There was a moment where the fraudster was trying to do something and we could just say no. And we would have prevented the whole thing. If we could go back in time, we could fix the problem. Shoot somebody's grandfather, classic 12 monkeys sort of financial engineering. So at this red line, at this current time here, we want to build a model that would teach us what to do. But we only have the data from now. We need the data from when the prevention was possible for all these different users, and that was at different times. But almost always, if you use a database and you have customer records or something like that, somebody will fix the data for you. They will clean it up. They will do master data management and reconcile what are the same accounts. If you want to find identity fraud and somebody is reducing everything to the single identity, you lose your chance to find it. If you're trying to do financial fraud and somebody corrects the errors that the fraudster made, you cannot build a model to detect those errors. So you need to know exactly what happened at the moment prevention was possible. Another simple thing is, suppose we're just analyzing how something responded. We sent an email to people, obviously not in Germany. In the US, we send an email to somebody and we get responses. And we send other emails and we get responses. And as odd as it sounds, I've seen marketing people go to a measurement at now, and they look at the number of clicks in the last hour and they decide which is the most popular. Now, if we have the graph of all time, that looks silly. But if we have only the graph, a bar graph, of course, maybe a pie chart, of that one moment, blue looks far better than anything else. As a person who likes numbers, I find this offensive. But it's what happens. Now, what we really want to do is wait a constant amount of time after the release for each one of those options. And then we would say green is far better. For that, again, we need a bit of a time machine. And this can be a very difficult query to write in SQL if somebody has corrected the data for us. I sound touchy about that. I have been the victim of corrected data several times and embarrassed myself in front of customers. So we need a time machine. And here's the example of the time machine. Let's talk about this streaming microservices. So we have a producer and a consumer. Makes sense. But the key thing here is that the producer and the consumer are now isolated in time. For microservices, they can be deployed independently, but now they can run independently at different times. The consumer does not have to run when the producer is producing data. The producer does not have to run when the consumer is consuming it. We have temporal independence. We also have geographical independence. The producer and the consumer do not even have to run in the same data center. It's very easy. The semantics of streams are very simple. We can replicate them safely. We could have an ocean between the producer and consumer, and nobody cares. Well, this isolation is very, very nice because if we have this stream of updates of business level events that are coming in, we can replicate the stream to an analytical environment, and we can use that to update a similar database to the production database. But we can go back in time and replay the past and stop it at any time. So we could play through all of history and find when we detected frauds. We could play through it again and stop it at each point when a fraud could have been prevented and look at the database and get the exact data as it was. This is a time machine, but a safe one that works with databases. So we need more than just files to do this kind of computation. We need tables and streams as first-class things. And they need to have names. They need to participate in all of the programming capabilities that we have for files. Okay, this is the last pattern. Simple systems are more powerful than you might imagine. And that could be simple advanced systems or simple systems, simple systems. So an example is we have a customer that does very complex engineering in the field and very customized, and they build ships with all kinds of measuring equipment on it. They build drilling equipment that automatically follows down and finds things underground. It's amazing. But in the first year of development, the single application that they found from machine learning that made them the most money was something that just prioritized accounting records for review. So what happens is somebody's in the field and oil is spurting and they fix this pump. So there's parts, there's labor, there's transportation, and some of that could be billed back to a customer or not. If the pump broke because our customer broke it by being stupid, the customer will not pay. If the pump broke because of normal wear and tear, the customer who wants the hole in the ground drilled will pay, or if it's part of a contract. If it is a normal maintenance operation, it goes into one category. If it is actually part of a multi-state thing, no taxes are paid on this. If it's single place, taxes are due. So the person in the field who has oil all over them and is in a hurry, what do? They're supposed to make these charges, and they take the first item on the menu, right? It's like, whatever, miscellaneous, which is usually the worst thing to do from an accounting point of view. Now somebody has to go back in and say, no, that was under this. this sort of thing. Somebody has to make a human judgment about it. But they can only review maybe at 1% or 0.5% of the transactions each month. So the question becomes, which 0.5%? If you could give the accountant the 0.5% of transactions or less that they should review, the most valuable mistakes, you can make a lot of money. How do you train that? Well, you just train it on all of the transactions, assume that most of them are right. So you have training data, you don't need any human judgments, you already have the human judgments, and in 1 month of development, they got to where they could save tens of millions of dollars a year. Now, this is almost embarrassing. You can't go tell your friends at the data science bar, oh, we made this accounting thing, and it didn't even make decisions. All it did is prioritize people to fix things. But that was the most valuable machine learning. So that's a simple application. Let me show you a simple implementation. Let's talk about recommendations. Lots of research here. The basic idea is that, I'll explain it here in 5 slides. It will be a little bit simplified, but not much. You have a crowd, and they have ways of behaving. If we talk about my music preferences, it's a mixture. If we talk about your music preferences, it's a mixture. She last night said that she likes anything with a guitar. It's a mixture. Everybody has these. But within any given piece of that, I have a pattern, he has a pattern, he has a pattern. We 3 may have the same pattern, but then other patterns as well that are different. So we need to find those patterns from the crowd, and then we need to observe a human for a little bit of time and understand what they will do. Here's an example. This is an example, by the way, of big data. Look how big it is. Ooh, 4 meters across. How many people have data that big? So Alice got an apple and a puppy. Puppies are so cute. Bob has an apple, and Charles has a bicycle. What do we recommend for Bob? A puppy. See, this is what big data can do for you. Now, it's not as easy as it looks, because everybody wants a pony. We could do a survey. Who wanted a pony when you were little? Come on. Old Shatterhand, Winnetou. Winnetou had a pony. You wanted a pony. Come on. So everybody wanted a pony. So Amelia comes in and says she wants a pony. Great. She's a user. That's all we know. We know nothing about her preference there, because everybody wants a pony. So those are the 2 statistical things we need to look for. Co-occurrence, like apple and puppy, and ubiquitous co-occurrence, which is a bad thing, like ponies. We can do this with co-occurrence. And we can do very complicated machine learning with the co-occurrence. So you can see, for instance, pony here co-occurred with everything, and there were 2 apple people, and therefore pony co-occurred with apple twice. It co-occurred with everything, so it's not interesting. But we can also do something very simple. We don't have to use fancy non-negative matrix factorizations or whatever is fashionable at the moment. We can simply look for the co-occurrences that are interesting, that occurred more than we would have expected. In this case, because it's a very simple, ridiculous example with cartoons, we only had apple and pony as the interesting co-occurrences. But typically we would find for any given thing the 50 or 100 indicators, as we call them, things that co-occur, perhaps co-occur before in time. And that alone is enough, because we can take that row of indicators and put it in a search engine. Now, a search engine has text, but now it has things, behaviors. When he comes to my website, I can take his behavior for the last 10 minutes and do a search for his behavior and tell him he wants a puppy, because I retrieve puppy from the text retrieval engine. And the text retrieval engine will actually do most of the weighting of these systems. Now, hundreds of companies around the world use this sort of technique. It can be implemented by an intern over a weekend. It's not complicated, which often means it's not prestigious. But the results can be very impressive. This is an example that we did many years ago with videos. And we took two kinds of behavior. One is the words people said when they searched for videos. The other behavior was the videos they watched. Not that they watched in response to the queries, they watched any time at all. The search query terms that they used any time at all, the videos they watched any time at all. If the same person in roughly the same month said a word and watched a video, that was a co-occurrence, a cross-occurrence, because it crosses from one behavior to another. And so then we used about 1 million videos. As far as we knew, there were no videos from Paco de Lucia. Paco de Lucia was a guitarist who was famous for what he called new flamenco, jazz-inspired Spanish classical music-ish. So when you put a query in for him, with conventional text, you would get hombres de Paco. De matches, Paco matches. 2 words out of 3 match. That's what textual retrieval gives you. But the recommendation-based search, where we say, what videos have Paco, De, or Lucia as indicators, is a very different thing. Here's the conventional retrieval. It's boring. It's hombres de Paco, 400 episodes or something. It's not funny after a while. Here are the recommendation results. Now remember, there's no correct answer. But what incorrect answers did we get? Top answer, it's very hard to see, but the guitar here is a semi-acoustic jazz guitar. And the music being played is classical Spanish music on a jazz guitar. Remember I told you what Paco de Lucia was famous for is jazz-infused classical guitar-inspired music. So that's actually a pretty cool hit. The next one's a little bit harder to understand. Ciudad, Bulería. Bulería is a flamenco dance. Ciudad is a dance group that dances to that kind of music. So that's actually a good hit too. The third one is just classical Spanish music being played on a classical guitar. The fourth one is Van Halen. A 20-second clip where in the middle of a song he started playing a little bit of classical guitar. Like, whoa, cool, crossover. And then the last one is somehow the most fun. It's a kid in a dorm room at university imitating Paco de Lucia. Now these looks like a system really truly understands what's going on. Nothing like that is happening. What is happening is we have very clever users doing what they want, expressing intelligence by their behavior, well, more or less intelligence by their behavior. And so we then reflect that intelligence back at other users and take credit. So he knows about music, and I say what he says to you, and you think I'm a genius. And we average out the noise and the idiocy. But this is the sort of thing that we can do with this system, and it really is not hard to build. So we don't need super amazing deep learning. Maybe simple deep learning is good, maybe cheap learning is more appropriate. So it's a lesson to be kept that we need to understand what actually makes a difference, what actually is going to help our system work well. And it usually isn't complexity, it's results. And the simplest, quickest way to get the results is, oddly enough, the best thing to do. So to review, lesson 0, definitely sweat the little stuff. Lesson 1, control the data as much as code. Lesson 2, we need something like Kubernetes, but for data. Lesson 3, we need more than just files. Files have been good enough for 50 years, but this idea that we have directories with only files, or we have tables with no directories, there was a fork in history. It was like science fiction, where one version of the world went one way, another version of the world went the other way, and history split. We had 1970, databases were invented, and right about then, Unix became aware, or the world became aware of that, and directories became a thing. But the database people never got directories, and the directory people never got tables. We need to fix that. We need to go back and shoot somebody's grandfather, and time will fold it together again, and we have files, tables, and streams in our file systems. Number 4, we don't need the fanciest deep learning, always. Sometimes we do, but often there's very simple things we can do that will give you almost miraculous results. So, I've talked about this in our latest book. Ellen and I have now written 10 books. I don't know how that happened. It was not the plan. The plan was to write one, but something got out of hand. And we've tried to encode and distill what we've heard from hundreds of customers about what made them successful in production. We also have the book before that about machine learning logistics, which talks about different architectures for deploying machine learning systems. And there were books before that, and books before that. We talked about the idea of asynchronous microservices in the streaming architecture. We talked about geo-distributed data in data where you want it. We talked about anomaly detection. Oh, look, one of those fish is going the other direction. That's so cosmic. And recommendations. Of course, everybody wants a pony, the pony book. These are all available for free from the MapR website in PDF form. If you catch me in a good mood, then I give them away as well. But the important thing is that they each are tiny. They're little bitty books. The longest one's 128 pages. Well, after the publisher did it, they didn't understand how beautiful 128 was, so they made it 136. But anyway, they're all small. That's the biggest one. The idea is to be one train ride or airplane ride in size and still say something that is now possible. Maybe it was an old idea, but it's now a good idea. Or maybe it's a new idea that can be done with our current systems. Those are all available now for free, as I said. And I would love to share them with anybody who wants them. And I would love feedback. If some of what they say is naive, please tell me. If there's something new that could make those better, please tell me. If you like it, please tell me. Love to hear from anybody. So we have 5 minutes, I think, for questions, roughly. Is that correct?